Hi, welcome back to the second lab of the series How to Start a Program inside the Smartfusion2 chip with the SMF2000. If you have not watched the environment setup video and the first lab in this series, please watch them because you cannot proceed without doing the previous two videos. So now, let's get started with the second lab. So in the previous lab, in the first lab, of this series, I already demonstrated step 1, step 2, step 3, step 4, and step 5, and the meaning of doing 5 steps. The first 5 steps is to get us similar to the liberal software, how to configure our Smartfusion2 chip using liberal and design and configure the chip inside liberal software and how to import it into the chip and see the program running on the chip. But for the step number 6 and 7, for the step number 6 and 7, if you already done through the lab 1, you will know that after finish the step 5, we'll have this result. I will show you the result of the previous lab. Okay, let's turn on. So this is the result after you connect the board again. If you already done the first lab and then you just connect the board again, you will see this is the program in the first lab. But the program in the first lab was imported directly into the chip memory and we cannot make any modification for that program. And the lab, this second lab with the step 6 and step 7, they show us how to write a program and import that software program into our chip. We don't use any pre-designed software program anymore, but we will design a software program ourselves based on some references software in SoftConsole software. So SoftConsole is a software that we need in order to write a software program and import it into the memory of the chip so it can do some specific tests with the board that the chip is located on. So now let's go to step number 6, and for the step number 6, mostly they will show us the steps in order to export the firmware and export some sample project. We don't write the program code or the C code in the SoftConsole from scratch, but we will use sample projects. But the very important thing is understand how to import the firmware based on the config, based on the design of our chip in Liberal, based of the previous lab. So let's open the Liberal and we wait for the Liberal to start. We wait for the Liberal to start. I just put this to show that there's something living around me. And we wait for Liberal. No. And we don't create any new project. We just open the project we already created in the lab number 1. Of course, you need to remember where you put your project. But my project will be here. This is my project, and this is the project file. You just need to double click on it to open the file. And we wait for our project to be open. And yes, now our project is already open. And this is the result of the previous lab 1. And to go to this lab, we need to export the firmware which is relevant to our configuration and design. Here we already made the design and the configuration for our chip. Now we want to export the firmware related to those already done, configured and designed. And we need to choose the config firmware calls. This is here. We right click and we open interactive. And again we wait. And this is the window we should see. Design firmware. This is the result you should see. If you don't have the same result, then you just need to click on the instance. When you click on the instance, there will be some something like yes, there will be some pop-up window asking that firmware is not in your vault. What is the job to do is just click on yes. So if there are any instance in this table which are not in the same status that you see in this video, please click on it, and there will be a pop-up window like this, and you just need to click yes for this pop-up window information in order to import that instance into the vault related to Libero, so Libero can recognize those instances now downloaded into the relevant folder that Libero can read from. And after those instance design cores already downloaded into the vault, now Libero can realize them. You will have such a status that Libero recognizes them. And then now we will have to check all of the information relevant to the things. For the Smartfusion2 CM60, this is the version we should have, and we can check it over here. I believe that I have the same version, 23105, 23105, correct? And now this is the step where we can generate a sample project. Sample project means a sample C code that we will use in the SoftConsole software to write a software program and import it into the memory of the chip, so the chip can read the program from the memory and execute it. And as they say that we need to click on the core PWM post width modulation in order to generate the sample project. And because our micro subsystem uses the microcontroller Cortex M3, so that's why they need to choose this option, and they choose the sample project. The sample project will evolve around the C language code. And now we generate it. We choose this option. We go to SoftConsole version 4 and we choose the slope link. And you need to choose the folder where we would like to export that sample into, and I would like to export it into the same folder of my project. And again, you can check this is the folder of my project, right? And I would like to export this SoftConsole sample code into the same thing. And you can see this is the file will be inside this new folder created into my existent project Libero. So I click OK, and this is the report of the generation. It contains all of the relevant file for this sample project, and we can click close. And we go back here, and now we need to generate another sample project related to the Smartfusion2 MSS RTC driver. So we need to choose the Smartfusion2 MSS RTC driver, and we right click in order to generate another sample C code or another sample project. Of course, Cortex M3, and we go to SoftConsole. SoftConsole is the software where we can design the C code, build, compile, and link the C code into the hexamal file and import that C code into the memory of the chip and run that program with our chip. And we need to choose the I think we need to choose the RTC, which is the project RTC TEM. Yes, the RTC TEM. Right click, and we need to choose the yeah, SoftConsole version 4.0, because the other one also for the SoftConsole 4.0 10. And it will be in the same SoftConsole folder inside my existent Libero project folder, and inside that SoftConsole there will be this second sample project, and I will click OK. And yes, the second project related to the TRC TEM also created in the SoftConsole folder. We can go to that SoftConsole folder and we check. These are the two sample projects generated from the relevant instance available in our chip. And after we already export all of the relevant sample project, now we will export those firmware configuration files and firmware drivers. We will need to export all of the firmware that relevant to the sample project. And to do so, we already generate the sample project based on the firmware cores that we have inside our chip. Now we need to export the firmware which is relevant to our design, relevant to our configuration and design that we made in the first lab. Right click and we export firmware. And the location also I would like to be in the same location as it's tested in the same existent folder of my Libero project. And the software IDE means the Integrated Development Environment. In other words, it is the software that enables us to write a C code, build, compile, and link to have the hexamol file, and let us to import that hexamol file into a memory so that file can be executed by a system, which is a chip in this case, which is our Smartfusion2 chip, to execute that C code. And we choose export hardware configuration and firmware drivers. The hardware configuration is what we were doing in the first lab of this series, and we will export the relevant firmware relevant to the hardware configuration. So everything is good. We just need to click OK and wait for the process to be done. And we should see that the firmware project was successfully exported to this one. It should be successfully exported. And we click OK. And here you can see all of the thing will appear over there. And if you undock it, you will see this is the datasheet relates to our design. If you remember, this is the design of our system, and the system means the system on chip Smartfusion2. And the important that we need to see is this one, is this map. This is the memory map where you can see the address of many components on the address bus, so we can interact with those components according to this address. And offset address is the starting address of that component. This is the starting address and this is the ending address. And with the starting address like this and the ending address like this, the memory that this component will take will be 4 kilobytes. And now let's move on. And we can see the firmware that we export and the sample project that we export from the file tabs in Libero. So we go back to here, we can just undock it. So it comes back to our main Libero window. And then we go to the file tab and we can see the firmware consists of all of the things that we just exported and also the SoftConsole over there. Maybe we can check whether we have the necessary thing. It seems we don't have those. We have those things, right? Drivers, firmware drivers over here. Yes, we have the firmware drivers relevant to all of the instances. I believe so. Core PWM, the GPIO, yes. The CMSIS, the CMSIS is over here, yes. The non-volatile memory, UART. So yes, all of the drivers are considered like the C library, where we can just use the API or the interface of that library in order to interact with those instances inside our chip. So we don't have to write those drivers from scratch. We can just use them, import them into the project and use them. And here they will show you that we need to look through the datasheet of our system design, especially the memory map, in order to know at which address that we need to talk to in order to interact with that component exactly inside the chip. And after we export the sample projects and we export the firmware relevance to our system design, then we can move on to the second step, which is the step number 7, where we will start to import the sample projects into the SoftConsole, and within the SoftConsole we can see that the program is written as the C code, where we can easily modify the content and use some relevant drivers that we already exported from the firmware of the design. Now we will start the SoftConsole to start our second step, which is design the software for our chip. In the lab number 1, we only get used to how to design, how to configure our hardware in the chip, but not the software. The software already provided with the XML file. But now in this lab, they show us what are the necessary steps that we need to do in order to write our own software program for the chip. And as they say that we need to create a workspace. A workspace is like a project for the SoftConsole. The workspace will contain all of the relevant folders or files that we need to create our own software for our chip. So we need to go to our existent liberal project folder. Will be here. This is our existing liberal project folder, and we can create a completely new project, and we say SoftConsole workspace, and then from the SoftConsole we will browse to that folder. It will be here. And this is our SoftConsole workspace. And we just need to launch it. And launch. And we wait. We wait. So the SoftConsole will start to be in that workspace. Now if you look at here at the header of the SoftConsole, they will say they are inside this SoftConsole workspace or inside this folder. So anything that we do over here will be saved in this SoftConsole workspace that we just created. And the next one what we need to do is to import the sample projects into this workspace. So we go to File and we go to Import, and we import the existing projects into the workspace. We click Next, and we need to browse to the root directory. I think that we need to browse to where we already import our sample project, right? So we need to browse to the directory that we import our sample project. And if you remember, when we import the sample project, we have the DILILLO to create a SoftConsole folder inside our existing DILILLO project, which is over here. We double click and you can see this is the two sample projects. We check this one, we select it, and we browse again. Maybe we can select the folder. No, you can only select one folder at a time. So we select this one to see. Okay, so we don't need to browse exactly to the sample project. If we want to import the two sample projects at the same time, we just need to choose this SoftConsole. We select the folder, and the two projects will be automatically recognized, and we just need to check them in order to import both of the projects into our workspace. And those options should follow the recommendation, which is by default, everything's by default, and we click finish. And you can see that in the project explorer over here, the two projects are imported. At the moment, I think if you read through this lab instruction, they will say we need to temporarily close this project because we don't use it. So we choose the project, right click, and we choose close project. Just temporarily close this project. So when we compile build project, this one won't cause any problem for this project, to avoid any linking problem between the two projects if they have some maybe similar name of files or folder. So that's why we better close the project that we're not going to work on at the moment. And next we will follow. We will need to import files into our project. We will need to import the firmware of our design into our project, because our project we need to use the drivers. You can see that there's the drivers over here, and of course the drivers should be up to date with our design, with our hardware design of the chip. In order to update this driver, we will click on the folder, right click, in order to import the newest firmware that we just exported from the DILILLO design. So we choose import and we choose file system. Yes, and then we will go to the firmware and to export the firmware. To the firmware folder, and we will need to check the folder that we want to import into our project. This one, driver config, and all. As the instructions say, we don't need to import the file list. They are not important, and we don't need to import those three also. And then we can click finish and click yes to all. So what we are doing, we are trying to update the drivers and the folders inside the project before we build it and combine it, so that the drivers that we are using in our software are compatible to the hardware design and configuration that we were already done for the chip in DILILLO in the first lab. So we say yes to all in order to update everything and import the new thing inside our design. And after we import the firmware, we can now look at the C code, which is the main program that we will need to build combined and linked, so that we will have the hexamal result file to import it to the memory of this chip, so the Smartfusion2 can start to execute this program. And they recommend to look at the platform.8 to check that this core PWM base address should start at the right address. How we could check it? We go back to DILILLO, we go to the reports where we have the datasheet, and we go to the memory map. The offset address means the base address, and the core PWM, yes, this is the component that we need to check. The base address should start from 5 and all zeros. So we need to fix it over here. If you scroll down a little bit, they also recommend the fixing to be the same that I'm doing. And after that, we can Control S to save our modification, or you can just go to File and save over here. But I suggest the shortcut Control S. And after we import every firmware necessary for our software project, which is the SlopeLink project, and also we check that the base address of the available components is correct according to the datasheet of our design system. Then we can start to set up the C++ build, because our program is written in C, so the building system for this C code should be set up probably. And we right click and we open properties, and you can see this is the, so what we are doing is trying to set up the C++ build appropriately for our C code. And we go to the environment. I'm thinking maybe we go to the setting. Maybe not maybe, we can follow this one, C++ build, and go to setting. And they say there are some configurations. Configurations mean whatever we are doing to modify inside this one should be for all configurations. If you see that there are two types of configuration, configuring for the C code to be built as a debug version, or the C code to be built as release version. However, there are some configuration that we need to do for both, so we should choose all configurations, so whatever we do will be applied for both of them. So now whatever we're gonna do will be applied for both configuration, release and debug. And for that one, we need to check the C compiler. And for the C compiler, we need to check that all of the include span should have those things. C compiler, the includes, they should have those things. System config called PWM CMSys, GNU Cortex M and HAL. We can check again system config called PWM CMSys, GNU and Cortex M3. So it's correct. They say if something missing, you can add the missing path by using this add button. This is over here, or you can see it's over here. You can add the directory. Maybe just copy, for example, if you miss this directory, or just go here and then you Control C, go back there, add, and Control V to paste it, and you click OK. But it's already there, so I could just delete it. Yes. And then that's the configuration that we need to do in the compiler for both configuration, release and debug. Or if there are some path that you say maybe it's not necessary, then you can click and you can edit instead of add a new one. And now let's go to the C compiler. For both configuration, we need to see the miscellaneous in the compiler. Yes, and we need to have this flag, and it's available already. That's good. And now we will need to do some specific configuration for the debug and release. They are not the same anymore. So that's why from here we need to choose the debug, some configuration that we would like to do for the debug only, and some configuration that we would like to do only for the release. So now let's do the debug first. And for the debugs, they would like to see from the linker. We should have this one in the script files, the linker in the general. Yes, from the linker to the general, and we need to have this one in the script files. Let's see whether this is the same. The debug will be in the embedded SRAM. Yes, for the debug, it should be in the embedded SRAM, which is correct. And now let's see. For the release, the same at the same area, we should have the embedded non-volatile memory. For the release, we should have it embedded non-volatile memory, and is correct. And after we already made the necessary configurations in order to build our project, build our C++ project, we can apply and close all of the configuration that we've done. And now we will right click and then we will build all. Or you can see that there's a build button over here, but just right click and choose build configuration and build all. And we wait for the building process to be finished. And you see that because we still on the process of designing or modifying the software program, the C code, to be imported into our chip. So now at the moment the chip only knows one program to execute, and that is the old program that we made in the first lab for the blinking of the area of the LEDs. When we start to import this software into the memory, you will see different program which will be executed according to this software. And after we build everything, we should expect no error. You can see in the problem tabs there are no problems, there are no errors, so that's good, as they suggest. And after we already built our project, now we need to configure the debugger inside the SoftConsole software, so that debugger can import our build project into the memory and start to run something. And to do so, we will need to go to the debugger over here. You can see the debugging, and we choose debug configuration, or we can go to the project and we choose run and we choose debug configuration, which is like this. Either you choose the program over here and you go to the debug, you go to debug configuration, you open it, or you can choose the program over here and you go to the run tab, you choose debug configuration. And we need to create a new debugger, and this is the step that they show in order to create a new debugger for our project. So we click on this one, right click, new configuration. You will see that is already linked to the project because we chose the project and then we chose run. So when we create a new debug configuration, it will be automatically detected the project that is linked to. And now we need to configure this debugging. We need to have this .f file in the debugger, but I don't have the same thing, so maybe I can just copy this one and put it in the C++ configuration application, so I can have the same result over here. And then I need to go to the debugger tab. I need to take the recommended option. We need to set the command over here in order to so that the debug can target the right device. So the debugger should target the right device, and in our case the device is the same. So we can check whether we have that one. No, we don't have it. It should be in the config options. We can just copy. Okay, maybe I can delete the highlight so I can easily copy things. Control C and Control V. They explain what are those commands for. So this command is to specify the target, and the target device means the chip. The target device means this chip. The debugger should target the SoftConsole debugger software should target which device, which is the M2S010, which is our chip over here. And this is the file for the integrated Cortex M3 of the Smartfusion2. We just need to follow, right? And scroll down to the GDB client setup. GDB means, I think this is the debugger. And we need to have this one inside the executable name. Yes, we have it. Cross prefix and cross suffix. And then in the commands we should have this one only, and delete the unnecessary one, otherwise they might cause some errors. We just need to keep the mem inaccessible by default off. So we should make the memory accessible, because if the debugger cannot access the memory, then it cannot import the hexamol file of our slowbring program into the memory, and cannot talk to that program in the debug mode. And now we can move on to the startup page, the startup tab inside the debugger, and do the two configuration as recommended. The startup, we choose enable ARM semi-hosting and uncheck the rerun and restart reset. It's good. And now we can apply. We applied all of the configuration that we done in the main, in the debugger, and in the startup for the debug of our sloping project. And then if we click debug, it will start to import the hexamol file which is already built into our device and start working. And if you look at the debug, if it goes like this and we go to problems, we have no problems, means it already good. We can change to the debug perspective from here. This is the debug perspective, and the debugger stopped our program. If you go back, you can see that the array of the LED stopped blinking. So it means inside the memory of our chip is already updated with the new program from this main C code. You can run step by step by using this. You can run this step by step and observe what is changing over here, or you can even observe from the register, or we can observe from the variables. And now we are running the program line by line inside the chip. So now whenever we click one line, it means we ask the chip to execute that line, the program that line, but not executing the whole program. If we want to execute the whole program, we can just resume, and then all of the program will be run. So now all of the program is executed by the chip. You can see only one LED is blinking over here. Now, to demonstrate that we are able to design the software for the chip, we can start to make the modification for the C code. We can go back to the C code perspective, and then we modified the delay count. If you modify the delay count, then we will change the rate blinking of this LED, if I'm correct, because they also tell us over here. Oh no, we don't change the delay count, we change the pulse width modulation period, which is here. If we make it larger, then the rate will be smaller. The rate will be smaller or slower. So we make it very kind of slow. Let's make it like this. I don't know the unit yet, but we just make the changing to make sure that we demonstrate we could design the software program ourselves and import it into the chip. We Control S to save it, and then we build the whole project again. We need to rebuild in order to make sure that the modification is included into our software design program, and make sure that there's no errors. Now we can start to run the debug again. We can choose the debug configuration. We choose this one, and we choose debug to run the debugger. We need to terminate this one before we run the new debugging process. And in order to terminate, we can go here, terminate and remove. We go back to the code, and now we will start the debugging again. We can choose the debug from run, and we go to debug configuration. We choose this one. Let's check all of the setup is good. All of the configuration is good. Yes, everything is good. Now we choose debug, and we wait so that the SoftConsole debugger will help us to importing the new C code into the memory, and we can change to the debug view. This is the debug view. And now we resume, and we see the result of our modification in the code. Now you can see that the rate of the blinking is very slow, and the rate of changing in the LED intensity are also very slow because of our modification in the pulse width modulation. So this is the end of the second lab. In summary, the second lab shows us the steps in order to design a software for chip in SoftConsole. And the first step we need to do, firstly, we need to import the firmware design relevant to our hardware configuration design in the DILILLO. After we export the firmware, we need to import those firmware into our software project in order to update all of the drivers to be compatible with our hardware design. And the next step, after we export the firmware and the drivers into our software workspace, we need to configure the C and C++ build system for our project so that our project will be built correctly inside SoftConsole. And after we correctly build the software, we can start to import it into our chip with the help of the debugger from SoftConsole software. And to run the debugger correctly, we also need to do the configuration for our debugger as they recommended inside the lab tutorial. And thank you so much for watching. If you find the video useful or helpful, please give me a like or subscribe, and see you in the next video. Goodbye.